At the annual Twins Convention in Minneapolis, there's a host of activities. The inevitable look-alike contest, a talent show, and even a visit to the ball game to cheer, who else? The Minnesota Twins. It's amazing how much some identical twins look alike. These similarities on the face of things make us wonder whether they're similar in other ways as well. In order to get beyond a visual impression of similarity, we've got to be able to measure it. Measuring in this case means examining characteristics that can be expressed as numbers, like height, for example. Here's a scatter plot of the heights of 17 pairs of identical twins. Each dot represents the heights of one pair of twins. There's a strong relationship. Now, if both twins in each pair were exactly the same height, the scatter plot would look like this. The points would form a straight line. With the actual height data, the points fall close to a line. So we say the overall pattern in these data is linear, and the association between the variables is positive. Both twins in each pair tend to be of similar heights. Here's another scatter plot. There's still a positive and roughly linear relationship between the variables, but it's less strong. The points lie less close to a line. The stronger the straight line relationship between two variables, the more closely we say they are correlated. In this unit, we'll learn to measure correlation with a number, the correlation coefficient R. R is a statistical measure of the strength of the straight line relationship between two quantitative variables. We'll learn some facts about R that help us understand correlation. We'll learn to calculate R from data. And we'll see that explaining a correlation can be controversial. Observing a correlation does not tell us why it is there. The correlation coefficient R gives us a numerical measure of the strength and direction of the straight line relationship between two variables. Let's look at some of the facts about R. R is always a number between -1 and +1. The closer R gets to +1, the stronger the linear association it describes. Notice that the associations here are positive. As one variable increases, so does the other. +1 is a perfect positive correlation, which means that all the points fall exactly on a line. In real data, perfect correlations are extremely rare. As R gets closer to -1, the linear association between the two variables again gets stronger. But this time, the association is negative. As one variable increases, the other tends to decrease. Returning to the scatter plot of twin heights, the correlation coefficient for pairs of twins is 0.92. Actually, this correlation between the heights of pairs of twins isn't quite the same as the R we'll learn to compute. That's because there's no natural choice of horizontal or vertical axis for the heights of two twins. Either height can go on either axis. But the properties of R stay the same, even though the calculation is different. In this scatter plot, the correlation coefficient is smaller, about 0.7. The larger correlation of heights, 0.92, reflects a stronger positive linear relation. The high correlation for heights of twins raised apart suggests that perhaps heredity has more to do with this characteristic than environment does. Since identical twins have the same genes, and since these twins did not grow up together, heredity could explain strong similarities between them.
You gonna hit the one ball? Hey, Jerry.
Mark Levy and Jerry Newman are identical twins who were separated at birth and adopted by different families in different states. They remained separated until a friend of Mark's arranged a surprise meeting. Mark recalls his first impression of his twin brother.
He's big like me. He's got a big nose like me and glasses like me. And he was wearing a baseball cap, and when he pulled the baseball cap off, I'm like, oh, hell, he's bald like me.
And that's when I said, Mark, I think Jerry is your brother.
And I said, no.
And then I proceeded to tell
Besides
Mark
their physical resemblance, which was even stronger before Jerry lost some weight, the two have a lot in common.
And
At the time of their reunion, Mark installed burglar alarms for a living. Jerry installed fire alarms. They're both bachelors with a passion for motorcycles. And both are fire captains at volunteer fire departments. A remarkable coincidence to outsiders, but not to Jerry.
Well, I guess I always wanted to be a fireman. It starts back when I was a little kid, back in Brooklyn. My father used to take me on open house to the local firehouse, and we used to go around the trucks and meet all the firemen down there. There was a fire call, and I heard the sirens, and we were close enough in the neighborhood, I'd always follow them.
We had 02. I'm pretty sure the wind put it up for the rain.
It's something natural. He's got to be a fireman. Only because firemen aren't made. Firemen are born. It's only natural that we both be firemen.
Mark and Jerry developed surprisingly similar personality traits independently of each other. Is this a simple coincidence? Or can their similarities be explained by their identical genes? This question is at the heart of a study of identical twins raised apart, conducted at the University of Minnesota.
And the first thing I need to have you do is to take off your boots, and then you decide who's going to go first.
This recently reunited pair is undergoing a week of intensive testing. The data gathered will be added to dozens of twin pairs already studied.
Not as tall as you look.
The question is, quantitatively, how much do twins really resemble each other on certain traits?
Great. These little ring fingers here are very...
It's a question of correlation.
Also, your thumbs are slightly different.
Yeah, but...
The director of the study, Thomas Bouchard.
The principal use of correlational techniques in our research with twins is as a measure of degree of similarity. The most interesting questions that we're trying to ask require that we divide the amount of variation that we observe in our samples of subjects between heredity and environment. And the correlation coefficient is a technique that allows us to do that. By quantitatively assessing the degree of similarity between our twins on various traits, we can, by further statistical techniques, actually say how much variation is due to environment and how much is due to heredity. But before we can answer that question, we have to get quantitative measures of similarity.
Subjects in the University of Minnesota study answer as many as 1,500 questions during their week of testing. Physical attributes are measured as well. Here, the subject responds to the anticipated stimulus of a balloon popping. Personality and intelligence tests are also administered. Comparative data on the same traits are gathered for identical twins reared together. And that brings the researchers to their central concern.
In the case of identical twins reared apart, the only reason they ought to be alike is that they share genes in common. So the measure of correlation or similarity between them reflects the effects of genes. The contrast is identical twins who are reared in their own family. There are two major reasons why they should be alike. One of the reasons is common genes or heredity. The other is common family environment. Consequently, you can compare identical twins reared together and identical twins reared apart, and the difference in the size of the correlation tells you the influence of the common family environment. So by simply comparing two correlations, you get a great deal of information.
This scatter plot illustrates the results of personality tests given to identical twin pairs raised apart. The relationship is not nearly as strong as the one for height, but the points do tend to increase together. The value of R is 0.49. For twins raised together, it's nearly the same, 0.52. One could interpret this as evidence that heredity plays a strong role in determining personality as well as height.
The correlation between the twins raised together was the same as the correlation for the twins raised apart. This suggests that whatever is responsible for the similarities in personality between identical twins is not the influence of the shared home environment.
Not everyone agrees with this interpretation of the Minnesota correlations. Some skeptics argue that separated twins went through the same adoption procedure or were placed in similar homes. So some of the effects the study assigns to heredity may actually reflect similar environments. As fascinating as it is, twin research is controversial. That's because heredity and environment are complex phenomena that are difficult to separate from one another. So even when a strong correlation is found, the obvious interpretation may not be the right one. Now, how do we calculate the value of R for a particular data set? This is the formula. It may look a bit overwhelming, but if we walk through it step by step, we can make sense of it. Here is a small set of data on two variables, x and y. The formula requires that we do some arithmetic on each point. You might recognize this term already. It's just a way of writing x in standard units. The value of x minus the mean of all the x values divided by the standard deviation of the x values. Next, we convert the value of y for this point into standard units in the same way. Using standard units means that the R we get doesn't depend on the units we use to measure x and y. If x is weight, for example, R won't change if we switch from pounds to kilograms. Since we're measuring the relationship between the two variables, we hook the x and y values together by multiplying the two standardized values. After we do this conversion and multiplication for each point, this sigma sign means add up all the products. If we stop there, R would be larger the more points there were. So we average these products. We divide by one less than the number of cases, or n minus 1. This also has the effect of keeping R between -1 and +1. In learning to use the correlation coefficient, we've once again emphasized combining pictures, here a scatter plot, with calculations, here the correlation coefficient, to help us interpret complex situations. But as usual, we've got to be careful in applying what we've learned. Here's a picture with a strong relation between two variables. But R, in this case, is 0. That's because R measures only straight line association, not association in general. In other cases, a picture can be misleading. Here's a scatter plot we saw earlier. The correlation is R equals 0.7. What's the correlation of this one? The points look closer to a line. But in fact, this is the same plot with more space around it. The space makes the relation look stronger. The correlation is the same, 0.7. The number helps correct the optical illusion. There's no doubt that identical twins are similar. Some even sway the same way when they sing. In this unit, we found that we can actually measure these similarities. And with the correlation coefficient R, we can quantify the strength and the direction of linear relationships. This is a valuable tool, but one that has to be applied with caution. The difficult work in statistics is interpretation.
Double trouble.
For any strong correlation, there may be various ways to explain it.